actually. So you have the ellipticals here, you have some irregulars, and you have these galaxies around here. But the point is that all of these galaxies, I am looking at them as, you know, they are the result of a bunch of different astrophysical processes that have happened throughout the history of the universe. So it is extremely important to understand exactly the variety that is around there so that we can test galaxy formation models. And specifically here, this talk, I'm interested in talking about stellar structure. And as you'll see, how much mass is contained in these stellar structures. And the main thing is that both the global and the more subgalactic scale of galaxies, these regions do actually tell you something about the past of these galaxies. Here's just a simulation of what should be happening in principle between the Milky Way and Andromeda when they get together and they end up destroying each other's disks. So that the thing is like you can have a merger that will destroy a very strong, stable, otherwise stable stellar structure as the disk is, but you can actually just completely destroy it through a merger. You can also, through minor mergers, so not something major that will destroy the disk, but you can also have minor mergers contributing to the growth of central bulges, transformation into other kinds of bulges, pseudo-bulges. And I need to read here because I cannot read there at the moment. The main thing is that the galaxy shapes will be associated to different past events. And also the persistence of some structures like bars does tell you that if you have a galaxy with a very strong bar, it actually is an indication that this galaxy has been not undergoing any sort of very grave action of merging action to have this sort of structure, but instead it has actually just grown slowly to what it is. This is just one of these results. This is work by João Nogueira Cavalcante. He was a PhD of mine a few years ago. And basically, this is just galaxies that vertigo of 0.8. So these pictures are merely to give you an idea of what kind of galaxies we're referring to here. He looked at the quenching timescales measured in based on spectroscopic indices that you'll hear about it a little bit more in the next talk by Thiago. But basically looking at mergers and also like elliptical galaxies actually do have faster, shorter quenching timescales. So the star formation will just use up all the gas much more quickly than the slowest ones around here are the strongly barred galaxies. So the main thing is like different shapes will actually point to different culprits, different things that actually happen. So it's not just looking at shapes because it's pretty, but actually because it features some information. And this work, I'll actually skip it for the moment because I know that Thiago will actually talk about Camila de Sanfreitas' work, also looking at morphology and how fast galaxies quench their star formation. So what I want to bring your attention to is what's actually happening at subgalactic scales in galaxies. So, but not just any structure. So looking at the structures that we most often find in galaxies. So when you think of a galaxy, usually well, there's a bulge or spheroid, there's a disk. Bars are very common. So these are the kind of structures that I'm concentrating in this talk. These are just two examples of two massive galaxies with a strong and not so strong bar. And the main thing about bars is that disks, kind of inevitably, they will at some point form a bar unless they have certain conditions that delay this process. Disks, they like forming bars. Bars actually do have a big impact in their host. They transport gas and stars also too, like throughout the galaxy, towards the inside, within the co-rotation radius, or to the outside if not. So it can actually alter the metallicity gradient. But there's a lot of things here that I list in this slide that are still under investigation. But the main thing is that, as I said, they like forming bars. So the presence of a bar will actually tell you that the conditions in the disk were fine to form a bar. And if there is not a bar in a disk, it means that it's either the culprits usually are, it's actually too gas rich. And by gas rich, I mean higher than 60% mass of the gas to the mass of the stars. It's dynamically hot. So you can think of it very simply, just instead of very rotationally supported. It has quite a bit of dispersion. You could think of it in that way. Or also it's a highly concentrated dark matter halo. So the presence of a bar is what I highlight here. Sorry. The presence of the bar, in a way, it tells you something about the maturity of this. So it's for this reason that work, for instance, by Chef already in 2008. It's been a while, but there have been other works that have done also similar work, but this was actually very thorough work, looking at the bar fraction as a function of redshift. So this is the age of the universe. If you want to see the original one, it actually went all the way to 0.81 in redshift, because this is using HST data, ACS, so they wanted to only trace up to the optical. We'll go into that in a moment. But basically, bars, just the bar fraction drops. And if you look at this in terms of different masses, so this is the bar fraction as a function of mass, and the different curves here, I'm just aiding a little bit to guide your eye. These are the very distant galaxies from the set. These are intermediate redshift, and these are local galaxies. And the main thing is that you can see that the high mass end, so these are the 10 to 11 sphere masses in these galaxies, they more or less, all of these massive galaxies already have their bars. Where you see most of the action, most of the change is really at the lower mass end. And this is not very low mass. This is still higher than 10 to the 10. We heard a little bit earlier from Virginia. She was talking about the barred galaxies in dwarfs. So this is even lower. They don't even appear here. But the main thing is that that you have a lot of this action in the low mass end of galaxies. So here, what we're interested in, and the work that I'm going to be showing it to you, has been something that has been developed through the years, looking at how much mass is actually involved in some of these structures, with a special interest in bars. Just for the sake of time, I will concentrate on that. The first thing is that we look at light. We need to transform that into stellar mass. We're not looking at a cosmological simulation, although I'm starting to dive into that. And it's wonderful because you get the mass. But when we're using observational data, then you need to actually make this transformation. And the argument really is to go to the infrared. It has less extension. I think that's pretty clear to this audience, probably. In the optical, you have a higher impact of dust obscuration. But here, when I'm talking about the infrared, we're looking at not so infrared that you're already seeing the emission from the dust, but that mid-infrared region, which is the sweet spot in terms of the mass to light ratio, actually varies quite a little, the very small amount of variation, independently of the stellar population that you're looking at. It really, what you are really looking at is the light emitted by the old stars that make up the bulk of the stars, of the mass of your galaxy. So what we need, so the argument is here, we need a big survey with a lot of morphological types that has very deep mapping so that you can really get to the outskirts of galaxies in the infrared. And this actually has been around for a while. I was part of this survey, the S4D survey. It's all available through IRSA, has been since 2013. So I do point you to that, go and take advantage of that, because it really is the deepest survey, all skies, so it includes galaxies in the south and north, at this bands, 3.6, 4.5. And basically, it goes to galaxies, it goes down to 1 solar mass per parsec square. So this is incredibly deep. It is not something that we can do from the surface of Earth easily. So this was done with Spitzer, when it was already the one Spitzer mission. So the cryogenic mission had already stopped, but it was still possible to use these hot bands. And it really does represent the largest, deepest, most homogeneous survey of nearby galaxies, going out to 40 megaparsecs, more or less, south to Virgo. And this is just to give you a sense. Many of you perhaps already know TUMAS. This is a survey that many of us have actually used. This in the near infrared, sorry, the HK bands. And when you compare this in galaxies, this is the images that you have from S4D. And you can actually see the same scale, so you can really go down quite deeply in this outskirts of these galaxies. So the motivation behind this program was to really kind of like map the endoskeleton of galaxies and get down to study the stellar masses in these structures. So what we have been doing, part of the S4G, as part of the S4G team, we did the composition that is available for you all to use if you wish. Just taking this as an example, you have your original galaxy and using a variation of Galfit, which is a 2D decomposition of galaxies. You can see here there's a model for a bar, a bulge, a disk, and then you have here all of them together. This represents the model that you have built, and when you subtract it, you can also study residual structures like rings, spiral arms, etc. So what we do is we actually look at how much light is contained in the 3.6, 4.5 bands, and based on our understanding of how this translates into stellar mass, we can talk about it a little bit more if you want. I have skipped those more technical details, but I can talk about them. Basically, just get a sense of how much mass is contained in each of these objects. This is something that we have done already for bars. We're doing this with disks and bulges, but the idea would also be to look at how much mass is typically contained in other structures. So this is work from this very talented student, Yasmin Coelho. She has been looking at bar galaxies. So this is just 3 examples out of the sample of over 350 bars in massive galaxies that she selected from, not that she selected, all of the bars in S4D that actually do have, they're not terribly inclined, because if they're too inclined, then we cannot really see if there's a bar. Well, looking at this, she actually, going through the decomposition, she looked at the masses in these bars, and this plot actually shows you how much, in terms of percentage, how much of the total mass of the galaxy is contained in the bar. And you can see more, it's approximately 10%, but here you can actually see how it's divided, what this mass distribution is like, for galaxies that are either also identified as having just disk, bar, and nucleus could be an AGN, it's just a point source. It's basically a non-resolved point source. Could also be a nuclear or starburst. In orange, you have galaxies that have been also described to be disk, bar, bulge, nucleus. This one, basically, the orange and the green, which is an here, also contain a bulge. And if you let these curves that I have drawn them just to guide your eye to, you can actually see that you have a tail of more massive, in the relative sense, the more massive bars would seem to be in galaxies that have bulges, sort of pointing to, well, then, as the galaxy goes through life, it's increasing. If nothing else is happening to this galaxy, its bar, it's acquiring mass, and you would find then more mature bars, if you will, compared in more mature galaxies that have bulges. So this is the kind of work that she's doing. She also looked it's not changing in either, so. Okay. ¿Así? Algo pasó. ¿Y sigo usando este? No, no estoy usando este. ¿Sigo usando este ahora? Okay. Yeah, no, I couldn't see a change here either. So, okay, so what Yasmin has continued doing, also this with Michael Grossi, who's a very recently hired professor at our institute. They also looked at all of the dwarf galaxies in this large sample of infrared data. And this is just to show you an example. Just this is how the dwarf galaxy looks. All those black spots, basically, they're just regions that have been masked due to like an intermeeting, like a foreground star, etc. This is the model that includes a disk and a nucleus. And basically, this is just in 2D. It's just an example of the kind of data that we're dealing with. And what they see, we first looking at the bar fraction, we heard this morning also how much fewer bars we find in dwarf galaxies. And it is quite notable, like massive galaxies, usually we associate 63, 65% of spiral galaxies contain a stellar bar. Not necessarily a strong stellar bar, but a stellar bar. And in dwarf galaxies, it's much lower, more around 15, 20. Here we identified 11%, and go into the details of why that is slightly lower. But the main thing is that this is consistent, this low frequency of bars in dwarf galaxies is consistent with this idea that you have galaxies at the lower mass end. They are still building their bars. They're still going through that process in which their conditions are sufficient to sustain a bar in that process of maturation. Looking at the bar, the mass content in bars, we're still first surprised when we noted that the quantity of gas that seemed to be contained in these bars in dwarf galaxies was actually pretty much the same as in massive galaxies. So it seemed like there was some, independently of how massive the galaxy is, the relative amount of mass that is contained in the bar was the same. So perhaps it was some fundamental physics. We got really excited until we saw, I mean, these are small number statistics. So there are a few, just 10, 11, something like that, galaxies. And when we actually just concentrate on more massive galaxies and look at how much mass is contained in their bars, you're just making the cut between 10 to the 10, 10 to the 11 solar masses and comparing to 10 to the 9 to 10 to the 10. So because we still have quite enough, the numbers are quite a bit, quite significant. We do see a tail that towards the more massive galaxies, you have more massive bars. So we go back to the expectation that low mass galaxies are still building their bars. So not only do they have less bars, they're less frequent, but also the bars that they contain, they seem to encompass less mass galaxies. So this is something that we have really just recently started since the end of last year. I had the privilege of going to the Flatiron Institute in New York. It was really nice, and I got to dab a little bit more in illustrious. And there's this student, I have two students, young students that are starting to work on this, Thiago Buenavalpias. He's just going into illustrious, and he's taking advantage of this really nice work from Rosas Guevara from this year, so very recent work, where they actually picked out at Z of 0 to the subhalos that contain strong bars or the spark galaxies. We are focusing in a sample of 50 strongly barred systems. And this is just an example. This is just starting. I haven't really. I'm just showing you this because it's something nice that we're starting. And if there are people working on illustrious, I would like to talk with you a little bit more. This is an example of one of these bars. This is just 10 to the 10, so it's quite typical. And just looking at the different stellar masses that are covered. So these are all massive galaxies, but this has been by choice. We have actually just focused now on these massive galaxies, and the idea is to implement the same kind of work that we did with the other observations and look at the mass contained and see how simulations are doing with respect to what we observe. So we're actually quite excited about doing this comparison. So I've been telling you, yes, morphology, look at morphology, shapes, they matter because they tell you so much about the process, but morphologies are tricky. We are looking at light and stellar populations. I mean, depending on what stars you have, you will actually have access to different parts of the galaxy, basically. And in the specific example of the bar, it has been no secret for a long time. We have known that if you look at a bar, this is in I band, you can see clear bar here. You can still see it in the B band, but if you go to the ultraviolet, you completely lose track of that bar. It's usually bars are composed of older stars, so they're not associated to strong UV emission. And if work that we have been putting forward, and should be submitting it pretty soon, is looking at bar properties as a function of wavelength. Here, basically, it's just tracing the toxicity profile as a function of semi-major axis, so distance from the center. And this is what you typically associate to the presence of the bar. It's monotonic increase in ellipticity and then a sudden drop when the isopods, the ellipses that are fitting to the isopods, they start fitting the disk. And if you're not in a very inclined galaxy, you will actually see such a drop. And what we noticed, or what we used, was looking at galaxies using S4D. So we have 3.6 microns, R band and B band to have deep. This is since galaxy, so this is deep optical data that we have. And what we see basically is that the bluer we look at the galaxy, the thinner and the longer it appears. I'm going to exaggerate this a lot so that you're right. That's what I'm saying. But you have a very kind of a very almost roundish bar that I've shown here. This is really exaggerated, but if the point is, I mean, you can actually have an impact of 20–25% in your measurements. And by bar strength, we measure bar strength. One of the ways that we can measure bar strength is the ellipticity, how thin it is. The thinner it is, the stronger it is. And the idea here, it's, I mean, how do we understand this? I mean, what seems to drive these trends? Well, the longer, why we see them longer, then you can, if you look at perhaps it's not as evident from that distance, but it's very common to find at the edges of bars, regions of active star formation. And these are brighter in the optical or UV light. So as you go to bluer, these ends will actually sort of stretch a little bit those ends of the bar, so it'll appear to be longer. So you would have your ellipses will continue, the isopod ellipticity will continue to go on for a little while longer. So this is why you have this kind of behavior. It'll actually stretch, and why thinner when you go to bluer. In bluer bands, the bulge will not be as prominent. So it kind of like the semi-minor axis of your ellipses will be limited by the size of your bulge. So if you're looking in redder bands, then you'll have a bigger bulge, kind of limiting how thin you can measure your bar to be. This seems pretty simple, but the thing is, like, we are just starting to look at bar properties at higher redshift. This is something that we have been looking at bar fraction at higher redshift, how this changes. But we're just starting to look at how bar properties actually change as a function of redshift. And we need to pay attention and actually correct those band shifting impacts. So this is the point of this work, to measure intrinsic changes in bar structural parameters at different cosmological times. We need to take into account these things. I actually, is it 35 minutes, Tanya? I have 35 minutes? No, but in total it's 35, right? Okay, yeah. I still have time. No, I was going to skip this because I thought I wasn't going to have time. But then I can just tell you that she was a postdoc. She actually left the team. So we have this incredible project that we need to finish. She left astronomy. So we're a great team. People don't leave us. They leave us to do other things and get more money. But anyway, so Villar Ramos, she did a really nice work looking at early type galaxies. So basically these are ellipticals and lenticular galaxies. And she used a sample of around 60. I thought I had to put it there, but anyway, they were around, the first in order. They're elliptical galaxies, usually they're sort of associated to us, so kind of like normal, nothing too exciting has happened with them in a while. But this is just a very simplistic view of them. We actually do know, we have known about this galaxy, for instance, NGC 0474. Already looking at SDSS, it was evident that there was a lot of things going on. This is not just an SDSS image, it's actually much deeper. But the point here is to call your attention to the different shells and tidal stuff that seems to be happening in these galaxies. So you look at this and you're saying, like, this is evidently not a boring system. A lot of interactions have happened in the past. And what she did was actually go use the S4D sample and identified just from the entire sample of early type galaxies, how many of these galaxies, by using the Gauss fleet decomposition that I described to you earlier to understand bars, she used this to kind of extract the smooth model and look at the residuals, and if she saw these ripples and these shells like this, then it was separated as a peculiar early type galaxy. And she found like it was just under 20%. These early type galaxies, it's consistent with some earlier work by the same group, by the S4D team that we had done in a smaller sample. But the first results, what she did that was new, was that she actually looked at the stellar population in these specific regions. So not only knowing, I mean, what we found out was that the mass contained in this region seems to be around, I think it was 13%. No, yeah, it wasn't 10% of the mass of the total mass in the galaxy. But she also looked at the ages in this. So she did this decomposition in different bands. So at 3.6, she used the ultraviolet. Because of the resolution, there was not that much information, but we could use it as a limit on how much UV emission could be associated to these regions, and also using the SDSS images. And what you find is that the star formation history pointed to a star formation event a few gigayears back, so 1 to 3 gigayears, which is consistent with the idea that these shells, they're not actively forming stars, but they are just remains. There's a persistence model of these shells, so they are just slowly dying away, but there's no active star formation associated with them. But it's a really nice project that we should be wrapping up at some point. And so our main interest has been actually to look at the distribution of mass in different stellar structures. I have focused here on bar galaxies because bars are simply ubiquitous, so they are a very interesting stellar structure that really alters the lives of these galaxies, of their host. But we have a great interest in also going beyond and understand the stellar population, so what the star formation history in these distinct stellar structures are. And we have, for that reason, we came up with this idea to go after all of the S4D galaxies. So remember, S4D is the Spitzer, this very deep Spitzer mid-infrared 3.6 micron data that goes down to 1 solar mass per parsec square. So this is the deepest tracing that we have of stellar mass distribution in nearby galaxies. So we said, let's go after these galaxies to that depth, the ones that we can reach from the south. So this is basically the summary of the Kanga survey. So those that have been in Brazil at some point, they know that Kanga can easily be associated to Rio, to the beach. And you always like your Sarang or Kanga to go to the beach. And this is the census of austral nearby galaxies. Clearly, we're going for the acronym, but it works because it's austral galaxies and they're nearby. Chiao and I, we are the PIs. This is multi-band, so this is GRIZ, deep imaging, also going down to the same mass surface density as S4D, using the SOAR telescope, 4.1, the 4.1 meters in Chile. We have access 30% of the time goes to Brazil, so we have been taking advantage of that. And the image quality and the resolution actually allows us to go down to a few tens of parsecs to up to 250 parsecs, depending on the distance of the galaxy, and really study stellar structure and also the details of the peripheries of these galaxies. We have a few science programs that have happened already. So we first focused on barred and ring galaxies. We also have looked at lenticulars, and right now we're finishing up on Milky Way analogs. We have now like 60 galaxies, but this is a long-term program. So the idea is to cover all of the S4D galaxies that are in the south. So we're talking about roughly 1,000 galaxies, a few hundred more. So it is a long-term campaign. And the idea is to combine this optical with the S4D to really, because S4D, the mid-infrared, does provide you with the best single band access to the stellar distribution in galaxies, but combined with the optical, you can really get a sense of what the ages of different galaxies, and if there are regions of new stars emitting in the ultraviolet, you recognize easily that, oh, that's going to be contaminated. But in the mid-infrared, you can also have emission from polycyclic aromatic hydrocarbons. So these are very small amounts of dust, and they can emit in the S4G bands. And in the if you have the optical too, you eliminate completely. You can really distinguish these ages. So the idea is really to get to the ultimate mapping of stellar mass in galaxies. So we're feeling quite excited with this. And this is just to give you a sense. I mean, the point is we'll have images of these galaxies, and we can say, well, this region here, it's younger than this region here. So we run Cigale, Lefa, and we'll actually be building these kinds of maps, stellar mass, star formation, stellar age. This is ongoing. This was one of the first galaxies that we looked at. And yeah, and the idea is to actually have this as a legacy for everyone, not just people in the south. But this is similar to the work, you could say it's similar to the work that has been done in the north with SDSS, but Kanga goes 3 magnitudes deeper. So the idea is to kind of do different science. And for something, since I have a few minutes extra, I wanted to call your attention to really nice movement that has been going on in Brazil. I don't know if you know about it, but it's a movement of parenting science. This started with a group of 5 professors in Urges, the Federal University in Rio Grande do Sul, 4 moms and 1 dad, academic people. They just started based on their own experiences. They were seeing how having children was having a huge impact in their productivity, but nobody seemed to be talking about it. I mean, those of you who have children obviously know I see my thing going like that, so we know this. And they said, let's just move beyond this anecdotal evidence and let's go for numbers. And they have been publishing a few papers on especially how the pandemic had a profound impact, especially on the productivity of mothers, but also what the impact of race, so all this intersectionality that needs to be considered. There was an ambassador program that started. That's when I joined, and I'm somewhere there. I don't remember exactly where, but so now we're almost 100 ambassadors through the country, and this actually is expanding. So there's a parenting science in Colombia. I don't know if there are people here in Argentina that want to talk to the parenting science movement, but this has called quite a bit of attention. They were awarded the Nature Research Award for inspiring women in science early last year. And yeah, they have been having a great impact in the system. So there's now the CV platform that Brazilians use to put their curriculum vitae. Now there's a space to put how long you spend on your maternity leave and things like that, so that when people see that pickup in your CV, they can actually see, oh, so this person was just not producing, I don't know, because they were slacking off or whatever. They had it, so that can be used for that. So it's just really giving a lot of visibility to that. And I thought I was going to have to skip this, and I am very happy that I'm 34 minutes, 20 seconds, so that means I can finish now. So this is my summary. Basically, the main things I wanted to take away from this is that we have a really nice group in Rio working on, one of the things that we're working on is how we can study galaxy shapes and the distribution of stellar mass in galaxies that we're doing very carefully to understand the formation history of galaxies, of different parts of the galaxy, and use S4G. This is picture mid-infrared data that is available to all of you. Just go to Google IRSA, IRSA, if you don't know about that, IRSA S4G, and you'll find it there. And yeah, and soon I hope we'll be able to show you more stuff on the Kanga server, which will be for everybody to use. So thank you.
Thank you, Karín. Questions? Thank you. Very nice talk. Interesting. My question is about the sample completeness. The S4G is not complete, of course, but when you present the fractions, for example, fractions of barred galaxies, are you correcting for volume completeness in this case?
So first, no sample is ever complete. We always define how complete it is. But so these are, I didn't mention them, but these are galaxies that are larger than 1 minute. Oh, sorry. Okay. It's list that I was trying to get there, but they're larger than 1 minute in size. They are within 40 megaparsecs. And the galactic latitude is also limited. I put it here. Yeah, this is the number I couldn't remember exactly. So, and they have big magnitude. So they're, I mean, you could summarize as the biggest and biggest and brightest.
Right.
But defined to this cut. So it does include dwarfs. What one of the things that we did realize was the original list of galaxies was based on H1, so radio coordinates. So we realized that we needed to complement because there were a lot of gas pool galaxies were not as well represented. That's not so much of an issue for your question. So the bar fractions that I mentioned to you, based on 2 mass, and the numbers that I showed you were based on HEC. The ones that we found, the 11% for dwarf galaxies, for instance, what we do realize is that it's lower mainly because of the approach that it was used for the decomposition. So bars that are, I guess, uglier or not as well defined, the Gulf fleet will not actually recognize them as, I mean, the model will not be as adequate, so they're just being classified as unbarred galaxies. So we think that's why they are, that we're a little bit under. It should be around 15%. I mean, what we find is 11% for the dwarf galaxies.
Okay. And just if you
sorry.
You have morphologies, yeah, for you. So what are the most common barred galaxies? SA, SC, SD.
So this was actually work by the Buddha 2010, I think it is, and he did this by eye. So I mean that's why we were using as initial morphologies. The morphologies that we have from, I mean from the decomposition, we don't actually have that distinction SA, SD. We just see, we haven't looked at where most of the bars are, but I guess if I remembered here by heart, I could tell you because this is previous knowledge, but I don't have it by heart, but certainly not at 0. So there are a lot of lens galaxies that also have bars. Yeah, I don't remember where you have more bars. This is also Peter Irwin from 2018. I can check in a moment and I tell you. Yeah. Sure.
Nice talk. Is there any correlation, or did you find any correlation between the bar length and the redshifts?
So we haven't. So that's one of the first things that people are also looking at. There was just a work by from Texas, the group. I have forgotten his name right now. Barazza, yeah. So Barazza et al. They looked at this, but only out to redshift of 0.2. So this was because they were looking at clusters, and they didn't see. They were mainly interested in seeing whether the bar properties were different in different environments. But they did trace out to 0.2, and the people who have actually started looking at bar properties, it has been mostly simulations. There is one work that started looking at this. This is very recent because I was talking to the person. I would say, but it's the only work that has actually started looking at higher redshift. Okay, yeah, I remember. So this is also from the S4D team, but I wasn't included. I wasn't part of that analysis. And they look using HST data. They look at bar properties up to redshift of 0.5, 0.8, and they don't see any significant change. But one of the arguments, and I was talking to the team and Kim. She was they didn't consider band shifting effects. So I need to wrap my head around it. I mean, they don't see anything. So if you correct for the band shifting effects, then in principle, if they are looking at bluer bands and they don't see anything, things are getting longer than perhaps they are tracing. If they correct for that, they would be tracing shorter bars. But a lot of work from simulations is actually looking at bar properties at higher redshift. So that's why it's so important to actually start to get the ball rolling from the observation side. Thank you.
Gracias. I'm curious. It's Andromeda. It's galaxy, very massive, very old, very spiral. No bar. Do we have an explanation for it?
I'm sorry, I did.
Andromeda has no bar. No bar. And it's spiral, massive, old, all the. Do we have an explanation or it's just el arroz negro en la sopa? Okay.
I am sorry, ¿me quieres hacer la pregunta en español? No estoy entendiendo.
Andromeda.
Andromeda, okay.
Andromeda, okay. Andromeda has no bar. But it's spiral, it's very massive, it's very
has all
whatever.
The qualities. Hard to explain. Now I understand it. Apologies, I was not understanding the first Andromeda, the word. So, yeah, it actually doesn't fall in any of those categories. So, yeah, good question. I don't actually personally know how to explain why it doesn't have a bar, because at these simulations, what they show is that unless it's like two gas rich, and not the case, and that's what we see more with dwarf galaxies. Where the explanations that we have of why we don't see bars there is that they're two gas rich. They also sent dark matter dominated. Many of them are like dispersion, dynamically hot. There was this work by Chef and Katzin in 2013, if I'm not mistaken, and they looked at with demos. They were looking at the velocities, so multi-slit spectroscopy, looking at how dynamically hot galaxies were, and they were seeing that being rotationally supported and dynamically cold appeared to be necessary, but not necessarily sufficient conditions to explain, to have a bar. So they did have other galaxies like Andromeda that they were dynamically cold, they were rotationally supported, they were massive, but they still didn't have a bar. So maybe the dark matter, I don't know, but the Andromeda is close enough that perhaps we could do something about it. I don't know. Perhaps somebody in the audience knows, but I don't know why Andromeda doesn't have a bar. It's a really good question. So as I said, it appears to be from this other paper that it would be sufficient, necessary conditions, but not sufficient. So you will not have bars in dynamically hot galaxies, but you can still not have a bar. Maybe it's just getting there.
It's the 40% with no bar.
Yeah.